Hello and welcome to this lecture where we're going to deal with simulation as a predictive modeling tool. This is the second of three themes. Recall that in the first theme we looked at data analysis, descriptive modeling, where we try to understand and describe the uncertainty that are embedded in random processes. This theme is going to look at predictive modeling, where we take that random process and we predict how it may respond to future interventions or to a future scenario. In the third theme, we're going to look at prescriptive modeling, where we become a lot more prescriptive and we apply optimization and specifically mathematical programming. Now, it is important from a learning outcome point of view that you understand the main elements of a discrete event simulation model. And we focus specifically on discrete event simulation in this theme, as well as at an undergraduate level, and then at an honors level we build on top of that, focusing a little bit more on agent-based modeling, which is a different form of simulation. You're required to be able to analyze the uncertainty embedded in a process. That's why we introduced the first theme, and then to apply that uncertainty by building, executing and interpreting the results of a discrete event simulation model. And you do that inside the software tool called AnyLogic. Now, the Personal Learning Edition or the PLE version is going to be more than adequate for you to solve the problems that we give you in this module. So the assessment is we give you a scenario and your job is to provide the decision support, meaning help the decision maker make a good decision based on the particular challenge at hand. And you're required to do this to write up your decision support or your solution in no more than 2 pages. Now, all of the past year's assignments are available with example memoranda. And I say example because there's more than one way to actually do this. We just give you one possible example. And these memorandums are available for you on ClickUp. For each of those past assignments, we will give you a project brief. We will give you all the necessary data as well as the assessment rubric on how that particular scenario will be assessed. So in this lecture, we're going to look at simulation modeling in general, delve a little bit deeper into discrete event simulation modeling, and then also talk about and demonstrate AnyLogic as our tool of choice. So in our context, we use simulation to imitate a real process. Now, this real process, there are uncertainties. Things are not 100% certain. There's complex interactions between process steps. And it's also important that you understand that you cannot necessarily describe the system in a closed form analytically. If you can do that, then don't use simulation. Just solve the closed form of the problem at hand. And if there are no uncertainties, then again, simulation may not be your tool of choice. So it is also important to know that when we introduce simulation, to acknowledge that simulation is not a silver bullet. So there are a couple of things to think about, and for each of these we make links to articles available for you on ClickUp. The first one is a paper by Centino and Carrillo from 2001 that gives you general guidelines on what simulation can, but also cannot do, when to use it and when not to use it. Biller and Nelson in 2002 wrote a good paper in terms of the importance of input data, why it is necessary to take your input data, the data that you gather and analyze and embed inside your simulation model, why it's important to get that right. And then Banks and Gibson in 1997 gave a couple of reasons on and evidence on when not to use simulation. And I highly recommend that you work through these papers to strengthen your base in terms of when to use this tool. But when it's applicable, it can be a pretty powerful tool to use. Now we talk about discrete event simulation. There are different forms of simulation, but very often long periods occur between things happening. And if you, let's say, model the growth of trees, you do not want your system state that you're modeling to every second say, has any tree grown? And 1 second later, check the state of the system, has any tree grown? but rather you only want to model very specific events that actually happen inside your process. So there are different ways, and discrete event simulation is shown to be a computationally efficient way of modeling random processes. So if you take the simple example of only two processes, A and B, and we assume that process A, the duration can best described by an exponential distribution with a lambda or a rate parameter of 0.1, and process B can best be described its duration by a normal distribution of a mean of 10 seconds and a standard deviation of 2 seconds. Now in the world of averages, this would be quite easy because the mean of an exponential distribution with a rate parameter is 1 over that lambda, and that is 10 seconds. And for process B, the mean of a normal distribution is just its mean, and that is also 10 seconds. So if you were to predict how this process, this random process will perform, you might say that no, there won't be any buildup of material at all. Process A takes on average 10 seconds. It will pass on the unit to process B, which will also take 10 seconds. And every 10 seconds, there's a part that is actually produced on this production line. But this is not the world of averages. And working with averages can be very dangerous. In reality, in such a little simple process, what you can expect is that there will either be a queue build-up in front of B, meaning A gives more units to B than what B can actually process at the time, or you might find that process B is starved, it's idle. It has capacity, but it's waiting for parts to actually arrive from process A. And it's because of these uncertainties and the interactions between process A and process B and the randomness inside these different process steps that simulation becomes quite valuable, that we want to predict, but what will the total production of such a little system be? And at this point in time, I want to illustrate the idea of a discrete event list and how a discrete event simulation model actually works. I want to point you and ask you to go and watch a video that I've recorded on specifically just discrete events, illustrating how a software tool like Simio or AnyLogic or Arena will actually represent the random process using these discrete events. Now, in the class example, assuming that you've got a basic understanding of these discrete event lists, we're going to simulate and build a model in AnyLogic where parts will be arriving, and then there is a manual process where these parts have to be kind of packed. You have to prepare them. You have to batch them in kind of a jig that takes 12 units at a time in a configuration of 3 by 4. And then this jig gets put into a CNC machine. Then you need to unbatch them, take them apart again, and then each one of those parts need to be inspected. And if a part passes, which happens 65% of the time, the part gets packaged. And once it's packaged, it gets shipped. Now, if the part does not pass the quality check, which happens 35% of the times, there's some manual rework that a worker can do and then re-inspect it again. After the rework, 10% of the units still don't pass and we have to scrap them. But 90% of those reworked units do pass, and from there they get sent back to the packaging line where they get packaged and shipped. So you get the idea here that there's quite a bit of randomness. The arrival rate can be random. The time that it takes to prepare the units are random. It's not 100% certain every time. The CNC machining may be very precise, but there may be some randomness in there as well. Unbatching takes some time. Inspection takes some time, which is also not 100% certain all of the times. It's also a random process. The fact that certain parts pass and other parts do not, that's random in itself. The reworking time is random. The subsequent inspection is random. So you get the idea that all of these steps inside this process concatenates, all of this uncertainty builds up, which makes it not so simple to predict what the total output of this particular production line is going to be. Now, those are the parts that we are processing. But there's another element. If we just have 20 workers, manual workers, and these 20 individuals are responsible for both the manual preparation and the manual rework, we may be interested to actually say, but how well is this group of 20 people, how well are they utilized? Do we need more, or are we overstaffed? Because if we're overstaffed, then we may want to relocate them to another area in our production line that may be starved and don't have enough human resources. Or if they are overburdened, at least we know by how much we can actually increase the number. And that's going to be the focus of our demonstration here, is how many of these 20 workers should we actually employ? Should we increase it? Should we decrease it and move them somewhere else? And we're going to use AnyLogic for that. Ultimately, what we're after is a graph like the one that we're demonstrating over here, where if we have 20 workers, we can actually see that the time for a part inside the system, their utilization is 99%, so they're completely overworked. And as a result, there's a lot of units that are stuck inside the process. 168 units at the end of a simulation run is what we have as work in process that does not get finished in a particular day. And we see that the time in system is roughly about 16, 17 minutes. But if we increase the number of manual workers to, let's say, 25, we can reduce their utilization to a lot more realistic 82%. And then at the end of the day, we can expect only 27 units to be work in process, which means our parts actually get shipped out the door. And we also see that the distribution of the time that parts spent inside this random process reduces quite significantly. Two good things happen. The distribution gets tighter and it actually moves lower in terms of the metric. So there's a 3-part video on our YouTube channel that we want you to work through that takes you step by step through the process of building this random process of parts being machined, batched, machined, unbatched, inspected, and possibly reworked. That will take you step by step through the process of building that in AnyLogic and finally preparing your data in a way that you can make such conclusions from it.